Hello, welcome to the ILS solution presentation. My name is Hugo Castro. I'm the Senior Vice President of Project Execution and Delivery for ETAP, involved in the design and implementation of ETAP real-time solutions. In this presentation, we will cover the following: the objective of performing load shedding, the characteristics of an ETAP ILS system, operation of the load shed system, the response time, how to improve the response time of ILS, validation and verification, main features and capabilities of ETAP ILS, and we will conclude. Why is load shed so important, and what is the objective? In any production or distribution network, it is critical to maintain the operation. We want to make sure that under any contingency, the critical and essential loads remain in operation. The load shedding solution that gets implemented must make sure of this to avoid interruption of processes that impact the production. Ensuring plant uptime and service continuity is important for the business. Also, when performing load shedding, it must interrupt the less load as possible. This means less loss of operation and therefore more production and, again, more profits. Having the proper load shed system also means less investment on power source backup or less contingency reserves, saving on fuel and investment. The ETAP ILS system meets the minimum characteristics listed below. It is built on the ETAP Digital Twin model. It understands every component capacity of the electrical network. It is fast-acting. We have tested response times less than 10 milliseconds. It's optimal. It has algorithms and engines that calculates the minimum amount of loads to shed. It is predictive. It determines if the system is going to be stable or not after load shedding. You can verify it, you can test it, you can repeat the tests, you can validate the logic, all integrated into one solution. It is scalable. The application has been installed from a small microgrid systems all the way to distribution networks and cities and large industrial facilities. It's redundant. All the components from the ILS controller to the action actuators and PLCs and RTUs are all can be configured in redundant configuration. And the system is very configurable. It has an editor that allows you to define the conditions and response time strategies customized to your system. The operation of the load shedding system in ETAP is as follows. First, we load the digital twin model of the electrical network. This digital twin model is built in the ETAP software. That model contains connectivity, capacity of every single component in the system, includes control models of generators, governors, exciters. It includes the dynamics, for example, of inverter systems, dynamics of motors, the dynamic response of the generators based on the control systems. All that information allows the ILS to understand the topology of the electrical network and the behavior of that network. In addition, we bring in the real-time data. The real-time data includes generation levels, includes loading conditions, includes configuration, meaning what is open, what is closed, load tap changer positions. We can bring non-electrical data such as the humidity, temperature, steam pressures, you name it, all that information that may be required to understand how the system is operating before any contingency happens. Then we feed the process information to determine the load priorities of the system. So we enter information such as process constraints. We define optimal groups of operation. This allows the load sharing system to determine automatically load priorities based on these optimal configurations. Then the ETAP load sharing system monitors disturbances in the network. Disturbances could be mechanical, it could be electrical. It includes failures in the control systems. For example, let's say if we're looking at a steam turbine generator and there's a failure on the there's a steam pressure drop, for example. The ILS understands that the capacity of the generation is dropped due to that condition. And you can also look at valve positions. You can look at temperatures, humidity, right, to derate the capacity of the generation units, and therefore determining, what is the available spinning reserve. So all of that information is captured by the ILS, including the electrical conditions such as generator trips, such as breaker disconnections, and used to determine when to initiate the load shedding. From this, we get the best combination of loads to trips. So the ILS controller determines the minimum load that needs to be tripped to maintain the stability of the system. And this stability is verified by the transient stability engine. Now, the operation of the ILS is optimal and can be adapted to many system architectures. In systems such as renewable systems, where there is low inertia and it requires near instantaneous response, ILS can be implemented in architectures using IEC 61850 communication protocols. This makes it very fast. We have measured response times in less than 10 milliseconds. The operation is started before any of the power sources feels any severe transient conditions. It is hardware agnostic. In this architecture here on the diagram, we see the ILS architecture built by the ILS controllers and by RTUs and controllers actually made by ETAP. But we have implemented this system with several vendors using IEC 61850. So it's hardware agnostic, and it uses the IEC 61850 Goose to make sure that communication is very fast and load shedding happens under the required response time. ILS has been implemented around the world with different hardware vendors under different architectures. In this particular case, ILS communicated to Schneider Electric's equipment to provide a solution to a customer in South America. Even in brownfield projects where we have incorporated ILS controllers to existing systems, ILS is able to achieve response times between 30 to 40 milliseconds. We have used different communication protocols, in some cases even Modbus, to communicate to be able to read real-time data, and Profibus IP, for example, sending control commands in a quick manner, still being able to achieve 30 to 40 milliseconds. So the architecture is very flexible and vendor agnostic. Now, why is it important to have high speed in a load shed system? In summary, it is because the faster the load is shed, the less load needs to be dropped. The idea is to balance load and generation as soon as possible. As you can see in the yellow line in this plot, the faster load is dropped, the system recovers faster, and there is less transients in the frequency response of surviving generation. The system frequency recovers faster. In addition, less load needs to be dropped to recover stability. Also, less load drop is required if the load shed is faster. ETAP ILS also has an integrated validation module that allows you to simulate the contingencies and see how the electrical network responds due to contingencies in the network. The transient stability is used to make sure that the ILS response will bring the system to stability. Note that the electrical digital twin model is accurate and can be tuned using applications such as dynamic parameter estimation tuning to make sure that the generator control models and any other dynamic components are simulated accurately. The configuration of the testing can be performed in two ways. One is in software in the loop. And software in the loop means that the digital twin model of the load shedding system is actually built into the ETAP solution, and it goes in a closed loop manner. So the condition is simulated. ILS determines what needs to be shed, and it sends the shed commands. And then the transient stability module is in charge of determining if the overall process is stable or not. In the same way, we can also connect the ILS controller in a hardware-in-the-loop manner, where ETAP simulates the electrical network and ILS monitors conditions happening in the electrical network, where we, for example, can simulate the tripping of a generator or island it from the utility. That condition is seen by the hardware-in-the-loop system, by the ILS. ILS sends the commands to ETAP, and ETAP will tell you if the system will remain stable or not, using, again, the transient stability algorithms within the ETAP software. The process of the validation of ILS is described here. Typically, you start by preparing the load shedding schemes in the ILS software. Then the system is put online, and the ILS simulator simulates the individual contingencies in the system and determines the response. It determines what loads need to be shed. That information altogether is transferred to the transient stability engine. The transient stability engine simulates the conditions and determines whether the system is stable or not. The results are analyzed by the engineers, and you can move on into the hardware testing. Once that information is passed, you can do hardware testing using hardware in the loop. The controller is deployed, and as the system it keeps evolving, and load shedding schemes have to be updated due to process changes or electrical network upgrades. You can continue with this life cycle of validation process in the ETAP. Note that you don't have, once the system is commissioned and the system is in runtime mode, you don't have to bring the ILS system offline to be able to test different schemes, to be able to simulate and validate them. And then with a click of a button, once the validation is performed, the update happens automatically without interrupting the process of ILS. So this is very important because it saves you time, it saves you money in the maintenance of the load shedding system. If you had a PLC-based load shedding, for example, you will have to invest time and effort to be able to put in a new logic into the PLC controller, be able to actually simulate it, test it, do hardware in the loop testing, do validation of the logic, and actually have validation of the logic, and actually have to bring the system offline to load the new program, bring it online. So all of that can be avoided by using the ILS solution. Here, let's look at the ILS viewer. If I wanted to validate, for example, this condition, I can go and just select it, right-click and select to run it in transient stability. The transient stability case is created directly from the ILS viewer. The information of what is shed, what is the triggers, all of that gets transferred directly to the transient stability. Here we're going to look at it manually. You can actually do this all automatic. However, I want to show you this. So in short, the benefits of having a load shed validation integrated into the system is saving time. You can model the system, you can put in the logic, you can validate it, verify it with a few clicks within the ETAP system, and make sure that the load shedding conditions are gonna be successful. The system is gonna be stable. You're gonna eliminate any potential hidden conditions. You're gonna be able to tune the logic very fast, and there's no additional investment or costly testing to be performed. Software and hardware in the loop can be tested within the same system. Coming back to this plot, one important factor also that is and is a very critical feature of ILS is the optimization engine. The system determines the optimal amount. The system determines the optimal amount of load to shed based on the condition of the type of disturbance of the system, looking at optimal performance based on available spinning reserves, looking at the control response of all the generators and sources in the system. So it determines the optimal amount of load to shed, and since it's shed faster, system recovers much faster. You can see that the final loading, right, the final loading in operation is a lot more compared to if you, for example, using something like a frequency relay based load shedding, where more load needs to be shed because the system waits longer to actually perform the load shedding. In this slide, we can see the dynamic load priority tables in action. The ILS system is simulating every contingency. For every contingency, is determining how much load is required to be shed. Based on that load required to be shed, the software looks at the priority table and determines the best combination of loads to shed to match that requirement. This allows the system to determine the minimum amount of load required to be shed, optimizing the surviving load to making sure the system will remain stable. Once this combination of loads is determined, the controllers are armed. When a condition happens, the controllers just take action based on the predefined combination of loads to shed. So this process, although in the ILS controllers, it takes a couple of milliseconds, it will not affect the overall response of the system. Those milliseconds are not even part of the response time of the ILS, as this information is predetermined. So when a contingency happens, the action is just taken without actually any calculations happening in series. Another important feature of the ILS system is the multiple subsystem handling. The network topology processor monitors the electrical network. Based on the status of all the devices, the system tracks if any islands are created. The islands are then indexed and determined and associated to the different contingencies as well as the loads. So there is no need to do any programming on the system. Automatically, the network topology processor determines the islands, determines which generators belong to which islands. It determines which loads belongs to each island, and the contingencies are also tracked in the location. So therefore, if an event happens on island A, it will not affect the loads in island B. In this example, we can see a system that can actually be split into multiple subsystems based on the topology of these breakers. Based on that, we can see that if we look at the subsystem in the contingency, and we look at the subsystems of the loads, you will see that when those breakers are actually taking action, those subsystems are automatically updated. So the ETAP ILS knows or matches the loads subsystems to the contingency subsystem. One more feature to look at is the load shed notifications. The ILS system actually monitors the conditions in the network. In addition to the standard alarming, it also looks at the available load shedding It looks at the required load shedding, and then if the available load shedding is not enough to cover that required load shedding, notifications are created. The notifications are either displayed on viewers, either notified in the alarm system, as well as notified through SMS. We can see it on this screen. In this screen, we're actually notifying for these particular contingencies. There isn't enough load to shed. The values are marked in red. Also, a notifications is displayed on the screen, as well as it can be actually sent to the alarm system and notified via SMS. One more feature that I want to demonstrate to you is the event capture. Whenever a load shed condition happens, the load shedding engine actually tracks that condition, and it is recorded into the historian of the load shedding, which you can access very quickly through the load shedding viewer. You can go and actually look at the most recent load shedding conditions. You can also come in here, select a different date, look at the conditions that happen, and the program is going to show you which loads were tripped. Now you can see here that these loads look green. That means that the ILS system sent the commands to trip, and those loads were actually tripped successfully. Under certain conditions, it can happen that for any communication error or a wire is disconnected where the load shedding happened. Commands were sent, but they were not actually executed by the final component. So you can see that really quickly on the load shedding viewer. Another feature to look at is the automatic load shed schedule. In ETAP ILS, you can create unlimited number of load shed schedules that can be applied according to the time of day, based on seasons, based on different times, different days during the calendar year. The priorities, as we know, can change based on these conditions, and therefore the load shed schedules can be defined based on daily, monthly, yearly schedules, and it updates automatically. On this example, we're going to notice we have an active actual schedule called FAT schedule. I'm going to update this to a schedule number 2. We will notice the following. So schedule number 2 now is active. However, we have the automatic scheduling system online. So what that means is that we are going to actually look at the the actual schedule, and the actual schedule indicates that the FAT schedule is supposed to be active from the time of 12 a.m. to 12 p.m. Currently, in the time is actually 5 p.m. So therefore, the schedule should be the FAT schedule. So the ILS system periodically will monitor the assigned schedule versus the schedule that needs to be active. Once it detects that the active schedule does not match the actual schedule, it automatically switches it over. So you can see here that it came back to the FAT schedule. And another feature that has been added that I believe is critical is the capability of updating the priorities of loads individually in runtime without having to bring the system offline. This capability gives the operator the power to switch the priority of a load depending on specific conditions that may have not been taken into account while setting up the load shed condition. So those conditions can happen when, for example, let's say you have a damaged component and you're running a backup load, right? In that particular case, the backup load may not be was not part of the priority loads to shed, and now it can be included. In this example here, we can go and actually take a load and switch the priority manually. To do that, I right-click on the load, I select Override, I apply the new a priority and hit apply, we will notice that the system flags the a priority that has been actually put in manually. We update the runtime system, and just with those few steps, now we have updated the priority of that load. In summary, the ETAP ILS utilizes the electrical digital twin with embedded predictive analytics, optimization algorithms, and load shedding action validation. The ETAP's intelligent load shedding solution makes faster than real-time decisions. We saw that the system can actually take response in less than 10 milliseconds. So with this, we come to an end of this presentation. Thank you for your time.